This video presents some of the key concepts underlying the message passing model with applications to MPI. A computational model in general is a conceptual view of the different types of operations that are available to a program. Keep in mind this does not include specific syntax or programming languages, and it's meant to be independent or almost independent of the underlying hardware. Parallel computational models are used for design or high-level design of software, typically on parallel computers, but could apply to conventional single nodes as well. And these models are differentiated along multiple axes, such as shared versus distributed memory model. That means the assumption is that all the processes are running on different CPUs, and the CPUs have access to the same shared memory. Or it could be a distributed memory model where each CPU has its own independent memory modules, but then the software can exchange or move messages or share messages over the network to share information between the different CPUs. So notice how the fundamental structure between shared memory and distributed memory is different. And these computational models need this level of information for them to be meaningfully applied. The other one could be implicit versus explicit parallelism. Here, remember, with implicit parallelism, the programmer does not have to create subtasks or instructions. The CPU typically has all of the necessary capabilities to split instructions and find independent or concurrent instructions and execute them, possibly using multiple ALUs. On the other hand, with explicit parallelism, the programmer has to recode or break the program into different instructions or submodules and then give it to one or more CPUs for execution. And that is the key distinction between implicit versus explicit parallelism. The other one could be control or data parallelism, where you could either have task parallelism or control parallelism, where one data item is applied or run by independent threads or processes to perform different types of operations. That means they run different algorithms. Conversely, in data parallel, you have multiple data items, and typically you will apply the same transformation or same algorithm to convert each one of the input items to an output item using multiple threads or processes. And this distinguishes control and data parallelism. Ultimately, all of these conceptual computational models address the issue on how parallel units of execution access memory and perform operations in a consistent and coherent manner. The message passing model is a parallel computational model in which programs or parallel programs are organized as a set of interacting processes. Note that there are multiple independent processes that could run possibly on independent compute nodes, and they interact with each other. Processes interact or communicate each other by sending and receiving messages. So the exchange of messages is the most salient aspect of this message passing model, as the name suggests. And message is just a well-defined unit of data that can contain any information as determined by the program or the parallel program that's running. And some models deem this interchange of messages as accessing remote memory of another process. The key reason why we are learning about this message passing model is because it is one of the most widely used models in the industry today. And these concepts apply to many modern systems such as web servers and servers on the internet, the database servers, or supercomputing applications. So by learning this message passing model, you can apply these concepts to many other systems. So knowing the pros and cons of message passing applies and helps you learn and apply these to many other systems that are out there. So let's talk about the pros and cons of message passing model. The message passing model has several advantages. That's why it's widely used. First one is universality, where it's a good fit for most computers and more distributed computing platform. And of course, it can be adapted to shared memory, even though that's not the real focus, but it can be. It is very expressive in the sense that you can use this model for expressing almost all of the parallel algorithms that we know. And it provides all of the aspects of a parallel algorithm, and it provides like an anthropomorphic flavor, like a human-like flavor, which is useful for formulating parallel algorithms. Message passing models are actually easier to debug than shared memory. Typically, race conditions that arise in shared memory are very, very difficult. They're a nightmare to debug. And this is something the shared memory model, because memory access is controlled in the form of sending and receiving messages, it is actually much easier to debug. and it's very scalable. Typically, when it comes to horizontal scalability, it provides very good horizontal scalability and performing, and this is the most compelling reason for message passing. That's why a lot of the database servers, web servers, use this model. And it is scales to utilize a large number of processors. There are many programs that run on supercomputing platform that use 1 million CPU cores for solving problems. So this is a very scalable solution. Of course, there are some drawbacks. Keep in mind this falls in the category of explicit parallelism. That means a programmer may have to perform a lot of the task of developing and running a parallel workload. And the model falls in the category of loosely synchronized or mostly unsynchronized. So that means a programmer is responsible for coordinating or synchronizing different activities and things like that. Um, this model is not ideal for fine grained parallelism. That means if you're looking at very fine grained, like a microsecond level operation, this is not a good one. So you need to have a good balance here. You need to think of larger problems. And load balancing is not very easy. It's not too easy to just migrate a process from one compute node to another, things like that. So load balancing can be a bit of a challenge. And of course, deadlocks also occur in message passing programs, so it is the programmer needs to be aware of this. And of course, some of the drawbacks of the message passing model are advantages of the shared memory model, something to keep in mind as well. Let's look at the generic structure of message passing programs. Here, message passing programs are developed as asynchronous or loosely synchronous set of processes. This is to make it easy to implement parallel algorithms. And in general, the message passing paradigm supports different programs running on the different processes. However, in practice, typically a single program multiple data approach is used, where the same program is executed by all of the processes in the parallel program. Of course, keep in mind, even though it's a single program running and processing different data items, each process may perform a different task. And this is just a simple way, like you can use a series of if-else statements where you get the ID or the rank of the process. And based on the rank, each process can do a slightly different type of task as well. This is possible to get task parallelism out of this. There are different implementations that provide a practical approach for applying the message passing model. There are parallel programming languages, but they are few and lack like a general purpose applicability. So libraries are the most common and popular way of implementing message passing programs. And specifically, the message passing interface or MPI is now kind of become the gold standard on most supercomputing platforms to implement the message passing model and implement parallel algorithms. Let's look at some of the communication primitives in message passing model. Keep in mind, message passing model involves interactions by exchanging messages. So that means sending and receiving messages is the key operation. So we'll focus and talk about some of the different types to ways to send and receive a message. Keep in mind, in practice, these sending and messaging operations are performed very frequently. So that means they have to be implemented and optimized for efficiency. And optimizing message passing is a challenge because you have to deal with different communication protocols in the underlying hardware. You might have different technologies to connect the CPU to the interconnects or the networking infrastructure. There are different network topologies to deal with. And message passing programs may need some additional requirements as well. So we have to think about all of these in practice. However, in this presentation, we are going to abstract some of these details away. Yeah. So that means in a practical implementation, even though we are not going to talk, we're going to go over it in a more theoretical way. The practical approaches for message passing provide blocking, buffered and non-buffered operations, non-blocking and buffered and non-buffered operations. And a lot of them also support synchronous collective communication such as scattering, broadcasting, etc. But in this presentation, we'll just focus on these first two categories, which are the most generic and widely used categories and are widely supported in different paradigms. So keep in mind, with message passing operations, we're going to look at four key categories, um, both blocking and non-blocking. We're going to delve into the details of what they mean. And then in each one of these categories, they can be buffered or unbuffered. sends and receives. So this gives us the four categories that we are going to talk about briefly in this presentation. Specifically, when we talk about these categories, we'll talk about the complexity of these approaches on how to implement or support these approaches. We'll speak about how much extra memory is needed for these operations. We'll talk about idling issues that degrades performance. You don't want too much idling. And of course, issues with deadlocks and such. So we're going to talk about these four issues for each one of these four categories that we mentioned. Let's get started with the blocking send, receive, both buffered and non-buffered. Blocking operations is one of the most simplest and the most memory efficient inter-process message exchange. Here, the sender and receive synchronize before they send or receive. Keep in mind here, the sender and receiver will indefinitely wait or block for the other side to be ready to perform that operation. Keep in mind when the process is blocked or it's waiting, that means it's not doing any useful task and time is being wasted. That means you degrade performance. And some kind of a handshaking protocol is used to synchronize the sending and receiving process. And once the processes are synchronized, the data transfer happens. So let's look at it from a graphical perspective. Let's say in terms of time, there are two processes. In a simple case, there's one that's going to send, another that's going to receive. First, both the sending and receiving process are doing some computation. That's what the gray box shows. And then let's say the sending process needs to send a message. Okay, so it's going to call the send primitive. Then the process sends a request to send message to the receiving process. In this case, let us assume that the receiving process is ready to receive the message. It will send a OK to send. So here we are assuming that the receiving process react to the request immediately. So we are going to assume that neither of the process idles. This is the ideal scenario. This doesn't happen often in practice, but this is the ideal scenario. So once the handshaking is complete, that means you have a request to send that is being sent, and the receiving process says, yeah, I'm ready to receive. The data transfer happens from the sender to receiver, and then both the processes continue with their operations, with the sender doing some operation and receiver typically processing the message that it got. So this is an example, a conceptual view of how blocking, that means it's going to block, and you have non-buffered, there are no buffers in the middle, and the data transfer happens. Let's look at a scenario in which is non-ideal. That means when the sending process is ready to send, it sends a request, but the receiving process may not be ready to receive or may not be idle. It might be using the CPU. So the sending process has to idle for a while, and this degrades the performance before the data is sent. Similarly, the receiving process might do some processing, and then it says, oh, now I need some data from the sender process, but the sender may not be ready to send. So here the receiving process has to idle, or it's spinning around, wasting CPU time until the receiver is ready to send the data, and then it happens. So this idling, both on the sending and receiving process happens, and this is wasted time, which kind of degrades performance. And this idling needs to be minimized in order, we may not be able to reduce it to zero, but we have to minimize it for increasing performance and throughput in this setup. Also keep in mind, deadlocks can occur in non-buffered blocking send and receive. Typically, if the processes are not coded up right, in some sense that process P0 is sending data, both processes are sending data, or both processes end up receiving data, that will not work. And this way it causes a deadlock. Instead, when one process is sending, the other process has to receive. Same way, if one process is receiving, the other process has to send. So it is important that the program is coded right. Otherwise, your program will, the parallel program will appear to hang, or it'll simply, it's called a deadlock. That means send will not work because this will cause a deadlock to happen. The advantages of this model is the simplest and the most straightforward to implement. It can be implemented on all communication hardware and topologies. It is memory efficient because no additional buffers are used. So if you want to send large volumes of data, this is the best way to do it. So if you want to send gigabytes of data, the blocking non-buffered send and receive is the way to go. Of course, the disadvantage are the processes may block or idle for a long time. as well. And of course, deadlocks can occur in this mode. Let's look at what happens if you buffer these sends. It's still blocking, but we use a buffer for send and receive. Okay, and these buffers are used to address the idling bottleneck to minimize. We will not be able to eliminate idling, but we'll try and minimize it. Okay, buffers are typically used both on the sender and receiver side, and processes read or write to their local buffers, and they do not idle or block for messages if the buffers are not full or empty. And the operating system then arranges to have these messages sent and received asynchronously to the remote process. Um, let's look at how it operates from a picture perspective. So typically what will happen is when the sending process is done, calls the send primitive, the sending process basically simply puts the message to be sent in a buffer and continues processing. And then the data is sent by the asynchronously by the operating system to the receive process, where it will simply store it in a buffer when it receives asynchronously at the operating system level. And whenever the receiving process is ready to receive, it will call the receive primitive, and that data will be read from that buffer and given to the receiving process. So these buffers are used to minimize the idling time. Okay. Keep in mind, ideally, neither the sender nor the receiver will idle, but there are cases where the receiver will idle if the receiver wants to receive but the buffers are empty. That means the sender is not yet sent a message, the receiver will have to uh, idle for a bit. Conversely, if the sender may also idle, if the buffers are full, that means it's sending a lot of messages, the receiving process is not yet receiving, then the buffers at the sender side will become full and the sender will have to idle. Buffer overflows can also happen, or this might also cause deadlocks to occur. So, for example, let's say the sending process reads a bunch of data from a file and starts sending data. Keep in mind the buffers are a finite size. So, you might have 256 gigs or something like that in a buffer. If this buffer is full of messages, that means the receiving process is not yet receiving data fast enough because it's taking a lot of time to process. The sending process will fill its buffers and it will have to idle, waiting for the receiving process to catch up. So, in such cases, this sender has to block or wait until the buffer space becomes available, and this may degrade the performance as well. Keep in mind, buffering alleviates many common deadlocks, but it's not a panacea. That means it will not fix all deadlocks. Deadlocks can still occur, and this can happen when communicating processes attempt to read an empty buffer, and sometimes you can get into what's called a circular wait, and these kinds of issues can happen. And the programmer is responsible. Remember, we are talking about explicit parallelism, so the programmer is responsible for detecting and avoiding such situations. Now that we've looked at blocking sends and receive, now let's look at non-blocking, buffered and non-buffered sends and receives. Okay. Non-blocking operations, the key difference is they do not wait for the send or receive operation to complete. That is the key. In the previous one, remember, there is some synchronization or coordination that has to happen between sender and receiver. In this one, it is completely asynchronous. So what happens when this is they perform as much or as little of the send and receive operation that needs to happen, and then they continue with processing. However, the programmer is responsible for repeatedly sending and receiving data until the message passing is successfully completed. So a lot of times it will avoid deadlocks, but it delegates the overhead of ensuring semantic validity of sending and receiving messages to the programmer. Okay? And additional restrictions may be placed for non-buffered or non-blocking sends and receives, because messages being sent cannot be modified until the transfer is complete. So if you can't go and modify the message while the message is being sent on the network. So there are some restrictions in this model. Non-blocking operations do not wait for send and receive operations to complete. So with buffering and typical network hardware, the overhead of sending and receiving can be completely masked. So that means it will almost feel like you have a zero cost for sending messages when done right. Yeah. And also here, the modern network hardware is capable of performing all input-output tasks. leaving the CPU free for doing computation. However, overlapping or accomplishing this overlapping I/O with computation to maximize performance is still tricky and requires considerable thought and optimization from the programmer. Okay? And keep in mind, this approach does not completely eliminate idling. There are many scenarios where processes end up idling, waiting for messages to arrive from other processes. So it's a possibility. So you will not be able to you will not be able to reduce idling to zero. It's just you will be able to minimize it a lot. Keep in mind, even with non-blocking buffered message passing, deadlocks can still occur. Okay, so this occurs when one process wants to send a large mess to this process, and process P1 wants to send a large message to this process. Then what happens is the buffers on each one of these processes. Remember, every process has its own buffer. These buffers can get full, and once these buffers are full, neither of the send operations will complete, and the overall parallel process will simply appear to hang, or it'll deadlock. So still deadlocks can occur in this operation. To avoid deadlocks, there are a few rules of thumb. Keep messages reasonably small. If you want to send large data, fragment them into smaller chunks or blocks. And always combine sending and receiving of data. Don't just write a loop that only sends or receives. Combine the two. And this kind of a philosophy will help avoid deadlocks both in blocking and non-blocking buffered sends and receive operations. Right? Hopefully you found this presentation interesting, and keep in mind these operations are important from the concept of applying to many distributed systems like database systems, web servers, and for supercomputing applications.